Hello everyone, welcome back. In this video, we are going to look at problems from chapter 19C of your Atkins text. Before we go further, let's have a quick recap of the lecture video on 19C. In this chapter, we discussed about the same phenomenological equations, but from three different perspectives. The first one being the thermodynamic view. Here we looked at the solid particles in a solution tends to decrease their Gibbs free energy by maximizing their entropy. So as they disperse, get diffused or dispersed in a solvent, their entropy increases. Based on this concept, we determined uh, thermodynamic force, which is nothing but when the solid molecules tries to diffuse, some work will be done against the force, and we call that force as the thermodynamic force. And from which we derived few equations that relates the concentration gradient to the thermodynamic force here. And also we link the force to the drift speed. From the second perspective, which is the concentration gradient, we looked at different equations where we first considered simple diffusion, and we derived this equation which suggests that the rate of concentration change is directly proportional to the variation of the concentration at a particular point, and also proportional to the diffusion coefficient. We also talked about convective flux, where how the particles or solid molecules tends to diffuse if you turn on stirring in a solution, for example. So from based on convective flux, we also derive the generalized diffusion equation, which considers both simple diffusion as well as the convection. From these, we also derived two equations that describe the diffusion in one dimension and also in three dimensions. From the third perspective, we looked at the motion of molecules from the statistical point of view, where let's say the net displacement of a molecule happens by means of a small series of steps. So which we call as a random walk model, and which is given by this probability distribution. And from these, we also derived an equation called Einstein-Smoluchowski equation, which relates the step, the mean free path. You could say that, you can call that, and also the time each molecule takes for to make each step during diffusion. So we are going to use some of these equations in the problem solving. So let's discuss few discussion-based questions and then go to the mathematics. The first question, describe the origin of the thermodynamic force and to what extent can it be regarded as an actual force? We sort of discussed this in the lecture, but let's look at it again. So imagine if you have a box with a number density distribution from, let's say this is the x-axis, x is equal to 0 to some x is equal to a position, and this is the number density given uh, by the symbol n. We also discussed that the molecules tends to decrease their Gibbs free energy. Here we talk about in terms of chemical potential. Let's say we have a high chemical potential at x is equal to 0 and lower chemical potential at x is equal to a. So the molecules tends to diffuse from x is equal to a to 0. From the thermodynamics class, we defined the chemical potential mu as the molar Gibbs free energy, right? So we are talking still Gibbs free energy, but in terms of chemical potential. So when a particle moves from x is equal to 0 to x is equal to a, some work needs to be done. And the work is equal to the change in the chemical potential, d mu, but we can write this as infinitesimally small change in the chemical potential with respect to infinitesimally small change in the x times the overall displacement of the molecule. So this is given. So this is the equation for the work. But in thermodynamics, we also discussed that or what needs to be against a force, right, along some direction. If we compare these equations, let's say I call this as 1, and this is 2, and this one is 3. If I compare 2 and 3 equations, we can write the equation for force as minus dou mu by dou x. So that's the thermodynamic force. Make sure that it is at constant temperature and pressure. So this is one part. The question also asks about the second part. To what extent can it be regarded as an actual force? So this force is not like a gravity or magnetism, but it is simply defined as the negative gradient of the chemical potential, which is minus du mu by du x. So don't treat this thermodynamic force as a real force. It's just a convenient method to consider in understanding the motion of molecules. Next question. Account physically for the form of diffusion equation. So we in the lecture or from your text you can uh, read that we derived the fixed second law of diffusion, right? So we derived the second law of diffusion, which is given as dou c by dou t is equal to d times dou squared c by dou x squared. So what this tells is it relates the rate of change of concentration, which is dou c over dou t, to the spatial variation of the concentration at a point, at a particular point, let's say x. The curvature of the gradient, which is dou by dou x, dou c over dou x, we can rewrite this as dou over dou x and the derivative of c. So this is the curvature. Let's say imagine if we take this point and you measure the concentration at this position. Again, you measure another concentration at another position. Let's say this is A, B, and C. When you calculate the curvature of the gradient, if it is positive, that means if the concentration is higher at B, let's say concentration is higher at C than B than A, then the concentration from C tries to move into the point A and increases the concentration at point A. But if the this great curvature is negative, that means the concentration at A is greater than B than C, then the solid particles tends to move from position A to B and then to C. Thus decreases the concentration at A. So this is how we can account the diffusion equation physically to the motion of molecules or the change in concentration gradient. Next question. The diffusion coefficient of glucose in water at 25 degrees Celsius is 6.73 times 10 power negative 10 meters square per second. Estimate the time required for a glucose molecule to undergo a root mean square displacement of 5 millimeters. Again, as usual, we are going to note down all the parameters that are given in the question. So we have the displacement of the glucose molecule, a displacement coefficient, and temperature is given, and the displacement is 5 millimeters, and I'm converting that to meter square. Rather, it should be just meters, not meter square. So one equation that we know of is that links the the root mean square displacement x squared is equal to 2 times dt. Imagine a glucose molecule in a beaker of water. If you think about this, it is equally likely that the glucose molecule can displace in either direction, either x, y, or z, right? So, but this equation here only talks about the one-dimensional displacement or diffusion. So we need to calculate a three-dimensional equation or equivalent of three-dimensional equation. So for that, we need to make use of some mathematics, and let's deal with that. So I'm, I'm sure we all know about the Pythagoras theorem. Let's say, in this axis here, a molecule from origin 0 has displaced to a point in space in 3 dimensions. This molecule can would have gone from would have displaced in x direction, then come back to y direction, or they might have gone to z direction, again back to x whatever direction. Finally, it reached a point, and the displacement between 0 and some point A needs to be calculated, and in our case, it's just 5 millimeters. So the net displacement can be written as the displacement in unusual directions, right? So x squared plus y squared plus z squared. As I said previously, the molecule, it's the probability of molecule to get displaced in either of these directions is equal. So I can rewrite x squared as, I mean y squared as x squared, since both are they're all same. The final one is going to be 3x squared. And from one-dimensional equation, we know that x squared is equal to 2dt. Right? I'm going to multiply that here. So the final equation would be 6dt. So what's given here, right? What we need to find the time. We know the r squared displacement is 5. Let's cancel this. It's 5 millimeters. So to calculate t, it's going to be r squared over 6d. So let's do this math real quick. So t is equal to r squared is 5.0 times 10 power negative 3. That's the just displacement, so we need to square it, divided by the diffusion coefficient 6 times 6.73 times 10 power negative 10. Again, this is meter square per second. So if you solve this, you should be able to get the answer as 6.2 times 10 power 3 seconds. So from this equation, if we are given the time and the diffusion coefficient, we can calculate the root mean square displacement, or if you are given the root mean square displacement, we can calculate the time based on the diffusion coefficient. Next question. A layer of 20 grams of sucrose is spread uniformly over a surface of area 5 centimeters square and covered in water to a depth of 20 centimeters. What will be the molar concentration of sucrose molecules at 10 centimeters above the original layer at 10 seconds and 24 hours? Assume the diffusion is only the transport process, and that means which there is no convection involved in this, and the diffusion coefficient is given here. So to represent the question in terms of a rough diagram, again imagine a beaker of water where the bottom of the beaker is coated with the sucrose over an area of 5 centimeters square. What we need to determine is at different times like 10 seconds and 24 hours, what would be the concentration of sucrose at a height 10 centimeters from the surface, from the bottom surface, right? We know one equation that describes the one-dimensional diffusion equation. So in this case, we have to consider this one dimension because we are not talking about the concentration in any other direction, but just about the x direction, which is the height of the beaker. So it seems very straightforward. We have all of these parameters here. The mass is 20 grams of sucrose, and we need to convert this into moles because we have N naught in the equation. And the molecular weight is 342.30 gram per mole. Area is 5 centimeters squared. I converted that to meter squared. This is the diffusion coefficient. X is 10 centimeters. Again, can convert that to meters. and time is 10 seconds and 24 hours. Let's try to solve this problem. So first things first, we need to calculate the number of moles of a sucrose molecule. So N naught is given by 20 grams divided by the molecular weight, 342.30 gram per mole, which is nothing but 5.84 times 10 power negative 2 moles. So from here we know the rest of the equation. So let's try to plug in. So C at point 1 meter, right? Again, I'm sorry, this one needs to be 10 times 10 power negative 2 meters, which is zero point 0.1 meter. Let's generalize the equation where t time can be a variable because we need to calculate the concentration at different times but at the same height. So let's plug in all the other values where the number of moles is 5.84 times 10 power negative 2 divided by the area is 5.0 times 10 power negative 4, and then 3.14 times the diffusion coefficient, which is 5.216 times 10 power negative 9. Oops. Yeah, so this whole thing power half. I'm taking the time out of this parenthesis and then have it as a separate variable. Again, we still have the exponential times the exponential term, exp, which is minus x is nothing but zero point 0.1 meters, right? So that'll be 0.1 meter square over 4 times the diffusion coefficient, 5.216 times 10 power negative 9, and this whole thing multiplied by time. Again, it's still a variable. So let's simplify this. Oops. I'm going to explain about this. Okay. So we can imagine this problem in terms of our physical world. Let's say that you go to a Starbucks and then you order some coffee. You drop a cube of sugar into the coffee cup. Unfortunately, you don't have the stirrers, right? And uh, you sip the coffee. Would you feel any sweetness at 10 seconds or after 24 hours? That's the question. Basically, the question asked for. Let's see whether we feel sweetness or not. So once you calculate that little bit of math there, so the concentration at zero point 0.1 meters at different times can be rewritten as 9.12 times 10 power 5 mole per dm cube times the time which we need to input in terms of seconds, power negative half, times the exponential term minus 4.79 times 10 power 5, again times the time in seconds. So now the first condition is we need to calculate the concentration at t is equal to 10 seconds. If you substitute the time as 10 seconds in the above equation and then try to find the concentration, surprisingly you would find the answer as 0 mole per dm cube. So that means after 10 seconds, we are not going to see any concentration of sucrose at the height of 10 centimeters. And if you calculate this at time is equal to 24 hours, but before that we need to convert the time hours into seconds. So 24 times 60 hours, 60 minutes, and 60 seconds per each minute. That gives 8.64 times 10 power 4 seconds. So you plug in this value and then try to find the concentration. If you do that, concentration is equal to 0.0121 mole per dm cube. So if you even after 24 hours of waiting, the concentration is going to be still very less at a height of 10 centimeters. So one thing that you need to take home is diffusion is a very slow process. Diffusion is very slow. So if you think about running a reaction, you don't just leave the reactants in the solvent. You stir the reaction mixture, right, to get maximum yield and for a quicker reaction. If you don't stir the reactants, probably you will never get the completion of the reaction. Even if you did, you have to wait for a long time, maybe weeks, sometimes months. Other thing is, don't drink a coffee without stirring after adding the sugar. You're not going to taste the sweetness unless you stir the coffee. Let's look at the next question. Suppose the concentration of a solute decays along the length of a container. Calculate the thermodynamic force on the solute at 25 degrees Celsius and 10 centimeters and 20 centimeters. Given that the concentration falls to half of its value in 10 centimeters. Again, let's think about this problem in terms of a rough diagram. Let's imagine that this is the length of the container and the concentration linearly varies, which is described by this equation. C of x is equal to C naught minus AX, where C naught is the concentration at x is equal to 0. So C naught is the concentration. C is equal to C naught at x is equal to 0. And A is a constant and x is the direction, right? We can calculate the equation, the numerical value for A by the condition that the concentration falls to half of its value in 10 centimeters. So let's do that first. Or let's say, so at x is equal to 0, let's say this is x is equal to 0, and this point is 10, and this is 20 centimeters. If you think about the concentration, it's C naught at x is equal to 0, and it becomes C naught over 2 at x is equal to 10, and it becomes C naught over 4 at x is equal to 20 centimeters. So using the same analogy, so C of x is equal to C naught minus AX. C of C 10 centimeters is equal to C naught minus A times 10, which is equal to C naught over half. If you try to rearrange this and bring the A to the left hand side of the equation, then it becomes C naught minus C naught over 2 divided by 10 centimeters, which is C naught over half over 10, which is equal to 0.050 centimeter inverse times C naught. We can always convert this into meters, which becomes 5.0 per meter times C naught. So now we have deduced a value for the constant A in terms of the initial concentration C naught. So what we have to find is we need to find the thermodynamic force at 10 centimeters and 20 centimeters. So let's do that. So we know this equation F is equal to minus RT over C dC over dx. So we have to find the concentration gradient dC over dx. And we know that concentration is given as C naught minus AX. If you take the derivative of this one, the derivative of a constant is 0, and the derivative of the second term is going to be minus A. So dC over dx is nothing but minus A. But substituting this equation, maybe I call it 1, into the force equation, it becomes minus RT over C times minus A, and the final equation is ART over C. So we know pretty much all of these values. So let's try to substitute the numbers. A is 5.0 per meter times C naught. Gas constant is 8.3145 joule per Kelvin per mole, and temperature is 298 Kelvin. The whole thing divided by C. Again, I'm trying to write it in terms of the linear gradient. C naught minus AX. Well, I can rewrite A as again 5.0 per meter times C naught times X. Again, let's try to solve this a little more. So the entire numerator becomes 12.4 times C naught divided by, I can take the C naught common in the denominator so that it becomes 1 minus 5.0 times X. So we need to input X value in terms of meters. So this X and one C naught, the other C naught gets cancelled. So the final equation is going to be 12.4 divided by 1 minus 5.0 per meter times X, which we have to input in terms of meters again. The overall unit, so when you include X in terms of meters, this meter and this meter gets cancelled. So the overall unit is going to be kilonewton per mole. Make sure that you get the unit in terms of joule, joule, meter, and second. So try to convert this into newtons. You should arrive at this equation as in terms of kilonewton per mole. So as per the question, we need to calculate this force at two distances, right? Force at 10 centimeters. X is equal to 10 centimeters. If you try to calculate that, it becomes, you're going to get it as 25 kilonewton per mole approximately. And at F is under 20 centimeters, the thermodynamic force is going to be infinity. Just think about why this is so. At x is equal to 0, we have concentration C naught, and at 10 we have C naught over 2, and at 20 we have C naught over 4. The constant, the, the thermodynamic force depends on the concentration gradient between 2 points, or rather the chemical potential. If if you look at the difference between points x is equal to 0 and x is equal to 20, the concentration gradient differs by quite a bit. Now, the concentration of x is equal to 20 is just 1/4 of the initial concentration. So we should be able to observe a higher thermodynamic force. In this case, it's infinity. And if you compare the force between point 0 and 10, it's it's a lot, but it's some finite value, which is 25 kilonewton per mole. Next question. Suppose that the concentration of a solid follows a Gaussian distribution that is proportional to exponential to the power of negative x squared along the length of a container. Calculate the thermodynamic force on the solute at 20 degrees Celsius and 5 centimeters, given that the concentration falls to half of its value in 5 centimeters. So this is essentially just a similar problem to the previous one, but in this case, instead of a linear gradient, we are having a Gaussian distribution. So let's look at this problem. One thing we know is the concentration depends as C of x is equal to C naught times e power minus a x squared. So C naught is the initial concentration. C is equal to initial concentration at x is equal to 0. And A is some constant which we can find by the condition that C at 5 centimeters is going to be C naught times e power minus a 5 squared is equal to C naught over half, because the concentration gets half or becomes half of its initial value for every 5 centimeters, right? So if you try to calculate the value of A, so let's do this. So it's going to be C naught and C naught gets cancelled here. The C naught and the C naught gets cancelled. And it's going to be e power minus 25a is equal to 1 over 2. And I can take natural logarithms on both sides of this equation. It becomes minus 25a is equal to ln half, and a is equal to ln 2. I'm taking the negative sign on this side so that the ln half becomes ln 2 divided by 25. Make sure that you have the units right, and this is 25 centimeters squared. So I can convert this back. I want to convert one of the centimeter to meters, and you will come to know why I do this as we solve further into the problem. So it becomes 4 times uh, it's 4 centimeter inverse and meter inverse times ln 2. That's the value of A. So for brevity's sake, I'm going to rewrite the value of A again. So we found that A is equal to 4.0 times centimeter inverse meter inverse times ln 2. So we need to find the force, thermodynamic force F of x is equal to minus RT over C times concentration gradient dc over dx. Again, let's try to find the derivative of this. D over dx is equal to C naught times e power minus a x squared, because this is the Gaussian distribution of the concentration. So when you solve this exponential, this is of a times b derivative, which is a derivative times b plus b derivative times a. But here the first term is constant, so it's going to be, the first term is going to be 0 since C naught is a constant. And the second term, the derivative of the second term is given as minus 2 ax C naught e power minus ax squared. That's equal to, if you do the math and then change this to again the entire Gaussian distribution equation, RT over C naught e power minus ax squared times 2 ax C naught e power minus ax squared. So we can cancel most of these equations out. So this entire thing gets cancelled with this. And the final equation is going to be 2artx. So that's the equation for force. And from here, it's kind of straightforward. We can plug in all the values that we have determined. A is 4 times centimeter inverse, meter inverse, ln 2 times the gas constant 8.314 joule per Kelvin per mole. times the temperature, 20 degrees Celsius is 293 Kelvin. At the end, we have to input the distance in terms of x, and the input for x value is in terms of centimeters. So when we input the centimeters here, this 1 centimeter gets cancelled. That's the reason why I wanted to convert 1 centimeter to meters and keep the other centimeter inverse as such. So when you do this, you get 13.5 kilonewton per mole times x, which needs to be inputted in terms of centimeters. So for F at 5 centimeters, it's 13.5 times 5, which is equal to 67.5 kilonewton per mole. So that's the final answer. Next question. The diffusion coefficient of carbon tetrachloride in heptane at 25 degrees Celsius is 3.17 times 10 power negative 9 meters squared per second. Estimate the time required for HCCl4 molecule to have a root mean square displacement of 5 millimeters. This is sort of problem which we looked in the beginning of this video, where we derived an equation for the displacement in 3 dimension as r squared is equal to 6 dt. Again, we have to find the time it takes the CCl4 molecule will take to get displaced by 5 millimeters, given that the diffusion coefficient. So it's a straightforward problem. T is equal to r squared over 6d. R squared is 5 millimeters, but we have to convert that to meters into SI units, which is 5 times 10 power negative 3 whole squared, and then at the end we get meter squared because we are also squaring the units. Divided by 6 times the diffusion coefficient, 3.17 times 10 power negative 9 meter squared per second. So if you do this math, this meter square and this meter square gets cancelled. The time you get is 1.38 times 10 power 3 seconds. Again, I want to reiterate the fact that the diffusion is a slow process. To just get displaced of about 5 millimeters, it will almost take 1300 seconds. So that's kind of very slow. Next question. Estimate the effective radius of a sucrose molecule in water at 25 degrees Celsius, given that its diffusion coefficient is 5.2 times 10 power negative 10 meters squared per second, and that the viscosity of water is 1 centipoise. Again, the examiner tends to give a different units, centipoise, but we need to convert that into SI units. The question asks to estimate the effective radius or the Stokes radius A, given that we have the diffusion coefficient and the viscosity. So we know one equation, which is the Einstein relation, where A is defined as kT over 6 pi eta d, where eta is the coefficient of viscosity. For us, eta is given as 1 centipoise, which is equal to 100th of a poise, and which we can rewrite as 1 times 10 power negative 3 kilogram per meter per second. So I guess now we have all of the essential values. So we just need to plug in all this. Boltzmann constant K is equal to 1.381 times 10 power negative 23 joule per Kelvin. And the temperature is 298 Kelvin. The entire thing divided by 6 times 3.14 times the viscosity 1 times 10 power negative 3 times the diffusion coefficient 5.2 times 10 power negative 10 meters squared per second. Again, make sure that you calculate the units. If you plug in all these units here, and then you should get the effective radius A in terms of meters, which is 4.2 times 10 power negative 10 meters. If you want to rewrite this in terms of nanometers, it's going to be 0.42 nanometers. Next question. The diffusion coefficient for molecular iodine in benzene is 2.13 times 10 power negative 9 meters square per second. How long does a molecule take to jump through about 1 molecular diameter, approximately the fundamental jump length for a translational motion? So let's again convert the question into a rough diagram. Let's imagine that each of this dot is iodine molecule in a benzene solvent. We are given the diffusion coefficient here, and lambda is the molecular diameter. So this diagram is not scaled, but imagine that the lambda is the molecular diameter, and that's the length of each step that molecule jumps from one position to other position. And it also takes a time, approximately a time tau, to for each of this molecular jump. So we can rewrite the molecular diameter in terms of its effective radius, 2 times its molecular radius A. We know the temperature and the viscosity of benzene is given here. So we know one equation that relates the effective radius to viscosity and diffusion coefficient, right? And we also know that diffusion coefficient is related to the lambda square by tau t, the jump length versus the time. And this equation is called the Einstein-Smoluchowski equation. So basically, we need to find the tau value. So let's do some math. So for this equation right here, d is equal to lambda square by 2 tau. We can calculate, as we described here, lambda, we can read it as 2 times a. And we know a is given by kt over 6 pi eta d. And the final equation is going to be kt over 3 pi eta b. So we can substitute this, let's call it as 1 and 2. So, but in this case, we need to find the tau and not d. So let's take tau onto the left-hand side of the equation, and tau is equal to lambda squared by 2b. And lambda, it's going to be 1 over 2d times kt over 3 pi eta d whole thing squared. Now we know all of these parameters. We just need to plug in to solve the equation. Let's do that real quick. 1 over 2d, 2 times diffusion coefficient is 2.13 times 10 power negative 9. And the Boltzmann constant is 1.381 times 10 power negative 23. T is the temperature, 298 Kelvin. And the denominator 3 times pi 3.14 times the viscosity 0.601 times 10 power negative 3 times again the diffusion coefficient 2.13 times 10 power negative 9, the whole thing squared. So if you solve this, you get the tau value is equal to 2.73 times 10 power negative 11 seconds, which is approximately 27.3 picosecond. So for the iodine molecule to make a molecular jump, uh, which is lambda, a molecular diameter, it takes almost 27.3 picoseconds for each step. Next question. A dilute solution of potassium permanganate in water at 25 degrees Celsius was prepared. The solution was in a horizontal tube of length 10 centimeters, and at first there was a linear gradation of intensity of the purple solution from left, where the concentration was zero point 0.1 mole per dm cube, to the right, where the concentration was 0.050 mole per dm cube. What is the magnitude and sign of the thermodynamic force acting on the solute close to the left face of the container, in the middle, and the close to the right face? Give the force per mole and force per molecule in each of these cases. So let's imagine this is a container and there is a linear gradation, and the purple solution varies from left as we go from left to right. And we are given the concentration at the left and the right. So the left is zero point 0.1 mole per dm cube and the right side is 0.050 mole per dm cube. So by this gradation, we can estimate that the concentration at the center is going to be 0.075. So in other words, if there is a change in 0.050 mole per dm cube concentration for 10 centimeters, and for 5 centimeters, there is going to be a change of 0.025 mole per dm cube. And that's how we calculated this value. So if we consider this force equation, we need to find the concentration gradient first. So let's do that now. So it's dc over dx. The concentration gradient is, as we think about the right and left, it's 0.05 minus 0.10. That's the concentration divided by the 10 centimeters. I'm converting that to meters, which is 0.1 meters. If you calculate this, the concentration gradient is going to be negative 0.50 mole per dm cube per meter. And let's also calculate the value for R on T. So 8.314 times the temperature is 298 Kelvin. So make sure that you find the units later. So you're going to get as 2.48 times 10 power 3. It's joule per, oops. You're gonna get this as Newton meter per mole. Make sure that you get these units tried out. So now we know RT value and the concentration gradient. So we need to calculate the force at the left face of the container first. So let's do that. F at the left face of the container. So it's going to be negative 2.48 times 10 power 3. And this is in Newton meter per mole, divided by the concentration at the left face is 0.100 mole per dm cube. The whole thing times the concentration gradient that we found is negative 0.50, and the units are mole per dm cube per meter. If you think about this, the mole per dm cube in the denominator, the mole per dm cube in the numerator gets cancelled, and the meter inverse meter also gets cancelled. The final equation that we get will be 12 kilonewton per mole. So this is per mole. The question also asks us to calculate the force per molecule. So we just need to divide this by the Avogadro number. So in that case, it's going to become 2.0 times 10 power negative 20 newtons per molecule. So this is at the left face. We also need to calculate the force at the right face and the middle. So the force at the middle position of the container is going to be 16.5 kilonewton per mole. In terms of per molecule, it's going to be 2.7 times 10 power negative 20. and the force at the right face is going to be 24.8 kilonewton per mole. Just do the same way as we did for the left. All you need to do is you need to change the concentration in the term, in the whole term. If you think about this in terms of newtons per molecule, it's going to be 4.1 times 10 power negative 20 newtons per molecule. So if you observe the trend, the force that is calculated as we go from left to right increases. And it's because there is a constant higher concentration gradient as we compare the leftmost point to the rightmost point. Whereas from the if you find the concentration gradient between left and the middle point, it's comparatively relatively lesser than the previous one. Next question. A dilute solution of potassium permanganate in water at 25 degrees Celsius was prepared. The solution was in a horizontal tube of length 10 centimeters. And at first, there was a Gaussian distribution of concentration around the center of the tube at x is equal to 0. And the Gaussian distribution is given by this function, with C naught is equal to 0.1 mole per dm cube, and A is a constant, which is 0.10 per centimeter squared. Determine the thermodynamic force acting on the solute as a function of the location x and plot the result. Give the force per mole and force per molecule in each case. What do you expect to be the consequence of thermodynamic force? So imagine, as in the previous problem, let's imagine this is a container which has potassium permanganate, but now it has a Gaussian distribution of the concentration, where concentration is highest at x is equal to 0 position, which is 0.100 mole per dm cube. We need to plot the thermodynamic force F as a function of the location. So let's solve this. Consider this again. C of x, the Gaussian function, C of x is equal to C naught exponential minus ax squared. We know C naught and A is also given, but let's convert A in terms of meter uh, per meter squared, which is going to be 0.10 times 10 power 4 per meter squared. The thermodynamic force is given as minus or negative RT over C times dC over dx. So first let's get this term. dC over dx is equal to d over dx, and C is nothing but C naught exponential to the power of minus ax squared. So let's calculate the derivative of this. When we do that, dc over dx is going to be minus 2axc. So let's substitute this in terms in force, which is minus rt over c times minus axc. So some of these terms gets cancelled, the c and c gets cancelled. The final equation for force is given as F is equal to it's 2a or tx. So from here onwards, it's a straightforward relation, and we know most of these parameters. So it's 2 times a is 0.10 times 10 power 4 per meter square times RT we calculated from one of the equations, which is 2.48 times 10 power 3. I'm sorry, like we calculated RT in our previous problem, right? So I'm just using the same value here, and the whole thing times x. So if you try to solve this problem, make sure that you calculate the units again. 50 kilonewton per centimeter per mole, and you have to input the x value in terms of centimeter, so that this centimeter and this centimeter gets cancelled, and the final equation you get is in terms of kilonewton per mole. So we should expect the force to be in some sort of in the units of kilonewton per mole. This is how you calculate the force in terms of per mole, but the question also asks us to calculate the force in terms of newtons per molecule. So in such cases, we need to divide our previous relation over the Avogadro number. So then it becomes, which is F is equal to 2A RTX over NA, which becomes 8.2 times 10 power negative 23 kilonewton per molecule. This whole thing times, okay, we also should include the centimeter inverse and multiply the entire thing by the position x in terms of centimeter. Let's imagine you calculate the force constant at every point. Let's say at x is equal to 1, 2, 3, 4, 5, and also at x is equal to -1, -2, -3, -4, and -5. And if you try to plot the force versus x, where it's -5 and it's here it's 5, the thermodynamic force is going to look like this. So if there is a huge change in the concentration gradient as we go farther from the central point of the tube, the force increases on either side of it. Since there is no net concentration gradient at x is equal to 0, the force is going to be 0 as well. So the last part of this question is, what do you expect to be the consequence of thermodynamic force? So a negative force will push the molecules to the left of the center point, and the positive force will push the molecules to the right of the central point of the tube. Next question. A lump of sucrose of mass 10 grams is suspended in the middle of a spherical flask of water of radius 10 centimeters at 25 degrees Celsius. What is the concentration of sucrose at the wall of the flask after 1 hour and 1 week? We are also given the diffusion coefficient of the sucrose molecule. So again, in terms of the diagram, let's imagine a sucrose mass is now hung in the middle of the spherical flask. We need to determine the concentration of the sucrose molecule at the wall of the spherical flask, which has a radius of 10 centimeters. So we know, and this is a spherical flask, right? So obviously the diffusion is going to be a three-dimensional problem. And the equation that we are discussed in the lecture for three-dimensional diffusion is this one. So it's kind of a similar one that which we looked for one dimension, but we're going to solve this for a three-dimensional case. So in this problem, first thing first is we need to determine the number of moles of sucrose mass. So N naught is equal to 10 divided by 342.30, which is the molecular weight. You're going to get this as 0.0290 moles. And we need to determine the concentration at 10 centimeters and at different times. So let's derive a generalized equation first, where we can input the time as a variable. So the moles is 0.0292 divided by 8 times 3.14 times the diffusion coefficient, 5.22 times 10 power negative 10, time to the power of 3 half. We also have a power to the entire, the terms in the parentheses, times there will be exponential term minus r is the radius, right? That is 10 centimeters. I converted that to meters. It's This should be 10 times 10 power negative 2, which is nothing but zero point 0.1, divided by 4 times 5.22 times 10 power negative 10 times t. As previously, we can substitute each of these terms for time. So our time t is equal to 1 hour. Make sure that you convert that to seconds, as we need to input the time in seconds. The concentration is 0.00 mole per dm cube. So as we also looked at a problem where we discussed about a Starbucks and coffee cup, it's kind of similar. So we're not going to see any concentration at the walls after 1 hour because diffusion is very slow. And if you measure the concentration after 24 hours, which is 6.048 times 10 power 5 seconds, the concentration of it is going to be 4.25 times 10 power negative 5 mole per dm cube. It's very less, right? Again, I'm going to reiterate this that diffusion is a very slow process. Next question. Confirm that one-dimensional diffusion model is a solution of the diffusion equation with the correct initial value. So the diffusion equation that we have seen from the text is dou c by dou t is equal to d times dou squared c by dou x squared. And this is the one-dimensional diffusion solution. So what we need to do is we need to prove that this indeed is the solution of this equation. It's kind of a bit intense with calculus, but let's solve this together. So first things first, there are many, okay, let's do this. We need to prove that dou c over dt is equal to d times d dou squared c by dou x squared. So let's first get the derivative of dou c over dt using c as this solution. But we will try to, make some of these constants as a single constant. So I'm going to rewrite the same equation as a over t power half times e power minus bx squared over t, where a is n naught over a times pi d power half and b is equal to 1 over 4d. So once we define this simple equation, let's calculate the dou c over dou t equation. So this will be dou over dou t times a over t power half times e power minus b x square over t. So again, this equation is in terms of a b derivative, which can be written as a derivative times b plus a times b derivative, right? So the derivative of this first term is going to be negative half times a over 3 halves. Again, we have to write b as b, bx squared over t plus, we're going to, the a is going to remain the same. So a over t half times the derivative of the second term is going to be bx squared over t, bx squared over t squared times e power minus bx squared over t. So this is the entire equation. Remember here, we are doing the derivative with respect to t and not with respect to x. So The derivative of this term is going to be bx squared over t squared times again the exponential. Again, further solving this, dc over dou t is going to be 1 over 2 t. I'm going to split this term here. I'm going to split this term t of our 3 halves into t half and t. So I combine that 1t here, and the rest of the terms is going to be a power t half times e power minus bx squared over t plus bx squared over t squared a over t half times e power minus bx squared over t. If you look at this equation, this this entire term is nothing but c of xt, or simply c, same as this one. This is also c. So I can rewrite dou c over dou t as minus c over 2t plus bx squared over t squared times c. So let's call this as equation 1. Going further, now we need to calculate dou c over dou x. So remember, we need to prove that dou c over dt is equal to dou d times dou squared c over dou x squared. So let's do this first. Dou over dou x, and then c is nothing but a over t power half times e power minus bx squared over t. So here we are doing the derivative with respect to x. So x is contained only in one of these terms. So we don't have to worry about the other terms. And this is going to be a over t half times the derivative of the second term is going to be minus 2bx over t times e power minus bx squared over t. See, we have to calculate the squared c by dou x squared, right? So we can rewrite this as dou over dou x, again dou c over dou x. So now we will substitute for this term and this equation, and then try to again derive this. So looking at this, it's going to be dou over dou x, a over t half times minus 2bx over t times e power minus bx squared over t. Again, we have x in this term, another x in this term. Now this is again AB type of derivative. So let's calculate the derivative for the first term here. Let's say this is the first term. It's going to be a over t half times minus 2b over t times e power minus bx squared over t plus. Now let's calculate the derivative for the second term, which is going to be a over t half times minus 2bx over t, again minus 2bx over t times e power minus bx squared over t. Again, if you look at this equation here, this term and this term combines to give us their equivalent to c. And again, in this case here, this term and this term are also equivalent to c. So rewriting this, dou square c by dou x squared is equal to minus 2bc over t plus 4b squared x squared over t squared times c. Doing rearranging that in further, so we know the value of b, right? So which is 1 over 4b as we derived in the starting of this derivation. So it's going to be 4bt plus, and from the previous one, I'm going to convert one of the b squared into 1 over 4d. So the rest of the parameters are going to be bx squared over t squared. Converting one of that, it's 4 over 4d times c. So it's going to be minus 1 over 2 dt times c plus bx squared over t squared or dt squared times c. Again, I can take the 1 over d common out of this. It's going to be minus c over tc plus bx squared over dt squared, or there's no d here, dt squared times c. So if you compare this, let's call this as 2, compared to the equation 1, you will realize that dou squared c over dou x squared is equal to 1 over t, and this term in the parenthesis is nothing but dou c over dou t. Hence we prove, right? So we can rearrange this to dou c over dou t is equal to d times dou squared c by dou x squared. Hence we proved that the one-dimensional diffusion uh, equation is indeed the solution for the fixed second law of diffusion. Next question. Calculate the relation between x squared power half and x power 4 to the power 1 quarters for diffusing particles at the time t if they have a diffusion constant d. So this is a bit of a tricky problem, but it's not impossible to solve this. So from the statistical approach, we have determined that a probability for any molecule to get displaced by a distance of x is given as p of x is equal to 1 over pi d t power half times e power minus x squared over 4 dt. So if this is the probability, and if you want to calculate the root mean square displacement of x squared, we need to weight that term x squared by this probability distribution. So in mathematically, this can be done like x squared is equal to integral from 0 to infinity. We have to weight this term x squared by this probability distribution, which is pi dt times power half times e power minus x squared over 4 dt dx. We know that this is a constant, so it can come out of the integral. The x squared becomes 1 over pi dt power half integral 0 to infinity x squared times e power minus x squared over 4 dt times dx. And this has a form of a standard integral, which is equal to, oops, so which is equal to 2 times square root of pi times dt power 3 half. So I'm going to include this. So the whole x squared term is going to be 1 over pi dt power half times 2 pi power half times dt power 3 over 2. Again, most of these terms gets cancelled again. So 1 pi and the pi gets cancelled. dt power half and dt power half gets cancelled just to leave dt. And the overall equation is going to be 2 dt. That's the x squared. So similarly, we can calculate this for x power 4, where we need to weight this term x power 4 by the probability distribution p of x, which is 1 over pi dt power half e power minus x squared over 4 dt times dx. Again, we can similarly solve this equation too. So this is a constant, so it comes out of the integral. Again, 0 to infinity integral x power 4 times e power minus x squared over 4 dt times dx. This is again a standard integral which has a solution of 12 times square root of pi times dt power 5 over 2. Further solving this, x power 4 is going to be 1 over pi dt power half times 12 times pi power half dt over 5 over 2. Some of these gets cancelled, right? The pi and the pi gets cancelled. The power dt power half leaves us only dt to the power of 3 over 2. So the final equation for x power 4 root mean square displacement is 12 dt squared. The question asks us to find the relation between the x squared power half x power 4 to the power of 1/4. So to determine that, let's divide x power 4 divided by x power whole square and squared. So this is going to be 12 dt squared divided by, and x squared is nothing but 4 dt squared. We did that just to cancel out these common terms here. So dt squared gets cancelled, which leaves us 3. So now we can take 1/4 power root on both sides of this equation. Then it becomes x to the power of 4 and then to the power of 1/4, 1/4 times x squared. This will be 2 times 1 power 4, which gives us 1 power half is equal to 3 power 1 over 4. So the final equation is x to the power 4, 1 power 4 divided by x squared to the power half is equal to 3 over 1 over 4. So that's the relation between different kinds of mean square displacements as determined from the random walk model. Next question. The thermodynamic force has a direction as well as a magnitude. And in a three-dimensional ideal system, as we determined from one of the equations from the text, the force becomes negative RT, uh, which is the Kronecker delta ln C, and where the delta is given here. What is the thermodynamic force acting to bring about the diffusion summarized by 3D diffusion equation? This one. That of a solute initially suspended at the center of a flask of a solvent. So again, this is mathematically a bit intense, but it's not impossible. Let's try to solve this. So we know that the delta is given as, or rather, we need to find the force first. So which is minus RT times delta ln C. But what is this term? The delta ln C is nothing but I times dou over dou x ln C plus j times dou over dou y ln C plus k times dou over dou C ln C. So again, we need to find each of these terms first. 1, 2, 3. So let's try the first one. Dou over dou x times ln C, which is nothing but dou over dou x. I can rewrite this ln C. The derivative of ln C is nothing but 1 over C. Instead of C, I'm writing CRT times d derivative of CRT over dx. So we need to find this one now. So 1 over CRT. What I'm doing is I'm going to split this term by by multiplying and dividing this term by dou r squared. So the end equation is going to be derivative of C RT divided by dou r squared times dou r squared over dou x. So first, let's find these two equations. So dou CRT over dr squared is nothing but dou over dou r squared. I'm considering this entire term here as a some constant since it doesn't have any term r squared. So dou by derivative of c, which is a times e power minus r squared over 4 dt. So the derivative of this is given as 1 over 4 dt times a times e power minus r squared over 4 dt. Again, this is nothing but CRT, right? So I can rewrite this as 1 over 4 dt CRT. So let's call this as equation 1, or yeah, equation 1. And similarly, we have to calculate dou r squared by dou x. We know that r can be written as x squared plus y squared plus z squared. Oh, sorry, this is r squared, which is the equivalent of the Pythagoras theorem that we solved in one of the problems. So the derivative of this equation is going to be 2x with respect to x. So again, let's call this as 2 and substitute 1 and 2 in the initial equation, which is this one. So the dou ln C RT over dou x is nothing but 1 over CRT times minus CRT over 4 dt times 2x. Again, probably a lot of these terms gets cancelled. CRT gets cancelled. 2 and becomes 2 here. So the final equation is going to be minus x over 2 dt. So similarly, we need to, if you look at the previous problem here. We need to calculate the values for each of these terms. We just calculated for one. If you try to do this analysis over and over, you get dou ln CRT, derivative of ln CRT with respect to y is going to be minus y over 2 dt, and the derivative of ln CRT with respect to z is going to be minus z over 2 dt. So let's put all of these terms in back into the original uh, the derivative delta, delta ln c, right? So that's going to be minus I x over 2 dt minus j y over 2 dt minus k z over 2 dt. So I can take this 1 over 2 dt as common, or negative 1 over 2 dt as common, and the rest of it is going to be ix plus jy plus kz. So again, going back to the force equation, F is equal to minus RT delta ln C, right? So I can substitute this equation into here, minus RT times minus over negative over 1 over 2 dt times this entire term can be written just as R, which is the direction R, and the whole term is going to be, oops, so the force, thermodynamic force, is given as RT over 2 dt times R. So this is the final equation that we need to solve for. Next question. The diffusion equation is valid when many elementary steps are taken in the time interval of interest, but the random walk calculations lets us discuss distributions for short times as well as for long times. Use the expression p of n lambda is equal to n factorial over n minus n r factorial, n times n r factorial times n power n, to calculate the probability of being 6 spaces from the origin after 4, 6, and 12 steps. So we need to understand how the statistical view works. So imagine there is a container or a tube, and we have a molecule at some position, initial position here. So after some time, this molecule, let's call it as A, it gets displaced to some other position here. So according to the statistical mechanics, this molecule, this A particle, can move in small steps, right? So which means it can take a step from left to right, like let's say, let's call it as an R, which moves from left to right, but also it can take a step in the reverse direction from L to R to L. So the net result that's seen is a combination of the steps taken towards right minus the steps taken towards the left. So the net distance it takes for this molecule to go from this position to this position is nr minus nl. And assuming that for each step it takes a molecular diameter or a step called lambda, and if you want to calculate the distance between calculate the displacement between the 2 points, it's nothing but n lambda. So based on this theoretical ground, Statistical mechanics deals with the probability of taking those spaces, which is the net displacement, in terms of a factorial, like the steps that have been that the molecule has taken in a given amount of time. So this is the equation. And the total number of steps a particle takes is n, which is nothing but nr plus nl. And the net effect is seen as nr minus nl. The number of steps taken towards the right minus the number of steps taken towards the left. So from these two equations, we can rearrange and then calculate, derive another relation, which is, so when we talk about nr, from this equation, nr is equal to n minus nl. I can substitute for negative nl by means of this equation. It becomes n plus n minus nr, and 2nr is equal to n plus n. nr is equal to n plus n over 2. So let's call this equation as 1 and this as 2. Let's substitute 2 into 1. It becomes p of n lambda is equal to n factorial over n minus n plus n over 2, the whole thing factorial, times n plus n over 2 factorial times 2 power n. If you solve this a little bit, it becomes n factorial over n minus n over 2 factorial times n plus n over 2 factorial times 2 power n. So what the question asks, we have to calculate the probability of being 6 paces from the origin. So paces is nothing but n lambda, which is 6, or n is equal to 6 after different steps. That is, the total number of steps is 4, 6, and 12. So let's calculate the probability. So for the first condition, where probability is of 6 lambda, when n is equal, where n is equal to 6 and the total number of steps is equal to 4. So the probability is going to be 0, because it's physically impossible to be 6 paces away from the origin when the molecule takes only 4 steps. So it doesn't make quite sense. So the probability is absolutely 0. It's not going to happen. And thinking about the second condition, or the B of this, where n is equal to 6 and the total number of steps is equal to 6. So let's calculate P of 6 lambda. And we know our equation, right? It's 6 factorial over 6 minus 6 over 2 factorial, 6 plus 6 over 2 factorial, and 2 power 6. So this becomes 0 factorial, which is 1, and this is 6 factorial. So it becomes 6 factorial over 6 factorial times 2 power 6. It's 1 over 64, and the probability is going to be 0.01562. Similar way, we can calculate the probability for the third condition, where n is equal to 6 and the total number of steps taken by the particle is 12. So P of 6 lambda is equal to 12 factorial divided by 12 minus 6 over 2 factorial 12 plus 6 over 2 factorial times 2 power 12. So 12 factorial divided by, and this term here, so this term here is going to be 3 factorial. So 3 factorial, and this whole term is going to be 18 factorial. Uh, I'm sorry. So this is going to be 9 factorial times 2 power 12. So let's rewrite the 12 factorial as 12 times 11 times 10 times 9 factorial over 3 factorial times 9 factorial times 2 power 12. So this 9 factorial and 9 factorial gets cancelled. 3 factorial is 6. 6 12 over 6 divided is equal to 2. So the whole thing is going to be 220 divided by 4096. If you calculate this, the probability is going to be 0.05371. So this is how we can calculate the probability of a particle being displaced depending on the number of steps that it takes. Next problem, and this is our last problem for this video and this chapter. The diffusion coefficient of a particular kind of tRNA molecule is 1 times 10 power negative 11 meters squared per second in the medium of a cell interior. How long does it take for molecules produced in the cell nucleus to reach the walls of the cell at a distance 1 micrometer, corresponding to the radius of the cell? So let's imagine this is a cell with a radius of 1 micrometer, and the tRNA is produced, let's say, in the nucleus of the cell. If How long does it take for the tRNA molecule to move from the nucleus to the walls of the cell? Again, this is based on the three-dimensional mean square displacement, right? R squared is equal to 680 as we solved. Even though the problem looks a little confusing, we have to simplify it. So we are given the diffusion coefficient, displacement is 1 micrometer, converting that to meters. We need to find the time t. So t is equal to r squared over 60. It's straightforward. So plug in the values of r squared and diffusion coefficient. You should get this answer as 1.77 times 10 power negative 2 seconds. That's kind of, no, pretty uh, less. It's quick. If you look at this problem or the answer to this problem, the tRNA molecule to get displaced like 1 micrometer, it just takes like kind of less time. Probably the movement of the tRNA molecule is mediated by the enzymes, so that's why it's pretty fast. All right, thank you. That's our problem discussion. Hopefully, I'll see you some other time.